Welcome all from all over the time zones, the second webinar of this eSIM marathon. In this webinar, we have Vladek Gravinsky. We are very glad to invite him to give a short talk. And then after that, I will discuss about the submissions and different other things. To give a brief introduction to Vladek, Vladek is an expert in electron technology with a focus on CMOS, BiCMOS electrical characterization and compact model development. So he has worked in various institutions like ETS Zurich, the Swiss Federal Institute of Technology, and Motorola. And currently he is a consultant for the IHP Frankfurt, and the one who is one of our collaborations in this hackathon, and he has helped in SPICE, Verilog standardization and radio frequency by CMOS IC design enablement to this process design kit. And he is a senior member of IEEE, and he currently works as GMC Consulting, Switzerland, and he has a lot of various experience in various solid state device conferences and mixed signal, mixed design, integrated circuit systems, and different other things. So we are glad to welcome you, Vladek. So over to you.
Thank you very much for your kind introduction and inviting me to your hackathon introduction. I prepared a couple of slides briefly introduce European or IHP OpenPDK initiative, going through all the elements from technology, devices, and applications. As I was already introduced, I'm a consultant for IHP OpenPDK. I also coordinate some activities through Mosaic K Group, IEEE-DS, and if you want to contact me, you can use any of these emails. FOSSI platform, it's a great initiative, in particular eSIM, introducing almost teenagers, students, and young researchers to integrated circuit design, promoting open source solution for all the tasks we need to design the circuits. To be honest, I wish I would see such initiative like FOSSI, eSIM also in Europe, which is still not the case. We'll go through a couple of points. I will start with motivation. eSIM, again, it's a great initiative. Each time I'm introducing OpenPDK, I'm showing your platform as the front runner of all open source activities in our electric engineering domain. Then I will list all what we have around the globe supporting OpenPDK initiative, including access to technology, Skywater and Global Founders in United States. There are a lot of ongoing actions in Japan and China, and of course IHP at the moment is very first and only one in Europe, giving you access to the technology device and complete IC design flow. I will conclude with showing a roadmap and our plans for further developments, listing all contributing with appropriate acknowledgements. In Europe, we are facing really critical issue, or there is less and less teenagers, young students joining our microelectronic IC design domain. And this point was highlighted a couple of times while we have discussed European Chip Act. And Joe DeBock, VP of IMEC, was highlighting this issue around the globe. Recent statistics are kind of scary. Just in Europe, we are missing about 10,000 or even more engineers and technicians in our microelectronics domain. Recent statistics are bringing these numbers really to highest level, talking about 100,000 of engineers we would need in Europe. To respond to this or help solving this issue, your platform, it's unique, introducing all the students in the secondary schools, engineering schools and university, fostering application of open source tools. Again, this is great initiative. I'm glad to follow your hackathon, and I wish we could have something similar also in Europe or at international level globally. eFabless, together with Google, were very first to support OpenPDK initiative. They managed to set up open source IC design flow and enable OpenPDK for two processes, Skywater and Global Foundries in the United States. In India, we have also great initiative. They call this One Student, One Chip, and it's developing very fast. If you look at these numbers, they are talking about 10,000 students who are participating in the project, designing integrated circuit, different application from analog RF to digital using open source tools. Of course, majority of designs are with digital, with RISC-V open source processor implementation. They also open very first process, 55 nano meter at IC4 in China, giving access to low-cost access to the process with different options, including standard CMOS with memory, eFlash memories, and eventually 100 nano BCD process for automotive IC design. In Japan, they have similar initiative. They call this sushi. Who does not like sushi? But in this case, it's about source utilize silicon initiatives. And they are trying to break all the barriers to enable access to open PDKs, even IPs and foundries open PDK. All work is in the project progress, and I hope they will announce first open source PDK in Japan soon. Brazil, its other domain origin, joining OpenPDK initiative. They created a very first website. It's very local in Portuguese, enabling or introducing local students and researchers, young IC designers to the concept of OpenPDK and open source tools. I was glad to learn that you've spoken to L'Oreal's having a huge directory of online resources, podcasts, and videos also in Portuguese. I'm sure this will be beneficial to all our partners, not only in Brazil, but all Portuguese-speaking languages, regions. I was introduced as a consultant for IHP OpenPDK. IHP is a research institute for high performance microelectronics in Germany and Frankfurt on Oder. It's located at Polish-German border. So going to Frankfurt, I feel like home, just crossing Odra River, being on Polish website. IHP is well-established institute with complete infrastructure for chip manufacturing. They have 8-inch pilot line, which is industry standard grade. They manufacture 130 nanometer silicon germanium by CMOS process with different options. The full 8-inch wafer infrastructure includes also bonding, packaging, and they also allow access to the well-equipped methodology or characterization lab with high-end microwave and terahertz measurements equipment. The services are not only prototyping or multi-project wafers to manufacture OpenPDK chips, but they also offer commercial services, closing full cycle from system design, technology, circuit, chip manufacturing, and packaging. Just follow links below to learn more about all IHP facilities. And there is also a link to the events they are organizing, promoting OpenPDK initiative and open source design tools. Couple of details about IHP process. It's by CMOS process with silicon germanium option, which includes high mobility bipolar devices. This is unique option, not only at IHP or Europe, but I guess internationally. We are giving access to a process with SG13G2 option, and the bipolar devices are operating up to almost 500 gigahertz, so half a tera on silicon germanium devices. This is unique number, and there are no similar processes in Europe offering this quality of RF devices. All is based on standard CMOS platform. It's 100 nanometer CMOS with all active devices, including diodes, ESD protection devices. Sorry, it's too fast. MOSFET varactors, passive components, including thin film resistors and MIM capacitors. Depending on the options, we can go up to 7 layers of metallization. For SG13G2, we have also extra 4 layers copper for RF application. The next process is still on qualification and should be available early next year. Again, on each slide, I have set of list e-links where you can get further information about discussed topic. The slide will be distributed among all attendees or participants after talk. We were running 3 OpenPDK multi-project wafer runs, mainly for analog RFIC applications. All were fully supported by local German funding. So starting with OpenPDK, open source design tools, submitting your tip, you were receiving as academic partner, you were receiving free silicon chip with your design. Unfortunately, we are closing these rounds for 2025. Last submission was September 15. We have open discussion and projects also for next year. In the meantime, we are offering low-cost open source multi-project wafer access for our 130 nano by CMOS process. It was announced as optional run for November. So this would be eventually a chance for you to submit your chips already this year. Now, IHP OpenPDK, all is free, available on GitHub. This is the summary of PDK context. As a designer, you have access to all complete database to start analog RF or digital design. We are providing base cell set for all design, including memory generators. They are primitive devices for all elements, including active and passive components like MOSFET bipolars. We include also reference measurement data. You can verify device performance. For layout, we are supporting open source K-layout tool, delivering full set of DRC text with minimal and complete. We have all parameterized Pi cells, Python-based digital cells. All the devices I have just mentioned, so MOSFET, bipolar, passive, are fully supported for transistor level simulation using ngSpice and ZICE. We have two options for schematic entry. It's eXiM and Quarks, which I will introduce just afterwards. If you are analog RF designers, you can benefit using OpenEMS. This is full 3D electromagnetic simulator, which you can use to validate your RF components. OpenPDK has a quite complex structure. We are supporting all different views. In this slide, process TCAD view, it's not really part of PDK, but it's important information for all who are working with process development, process enhancement, adding new elements, and using open source process and TCAD simulation tools. You can contribute to device level optimization. To start with your design, you access symbols view, starting with passive components like inductors, resistors, capacitors. We provide complete set of symbols for active components as well for basic digital block. Each element has this different view for numerical simulation, SPICE level simulation, or a Verilog A representation. After creating schematic, running device level or numerical simulation, you are coming to your circuit layout design. And we provide basic DDS2 layout blocks for passive components, active elements, and basic digital blocks. Free open source TCAD tools, great programs to understand or better understand device physics, semiconductor device behavior at a different level, from a very simple 2D representation up to complex 3D numerical modeling and simulation. If you are already running ngSpice, you can access device simulator called CIDR. There is just a simple 2D representation of potential distribution in the PN diode. DevSim, it's quite advanced 2D simulator where you can run, in this case, it's 2D representation of MOSFET device. Single device, maybe it's not enough to analyze more complex structure. Cogenda has TCAT has a 3D option, and here we have a 3D representation of basic SRAM memory cell. If you look at 2D representation, you can recognize drain, gate, source, or other way around with backside contacts. If you have a closer look, you can see these similar elements of MOSFET P and N type MOSFET in this complex 3D representation of memory cell. Again, this goes beyond standard PDK application, but it could be beneficial to all who are looking at device level simulation, understanding physics, trying to optimize devices for manufacturing. To start with free open source software for analog IC design, we have a couple of different options. Professor Rihanna at Stanford University, she was very first to set up such flow for analog RF design, starting with eXiHPM for schematic entry, ngSpice for transistor level, SPICE level simulation. She selected Magic, which is other GDS design tools. We recommend K-Layout, has all options for design rule checking, layout extraction, parasitic extraction. Then there are other options to run layout versus schematic verification before completing and preparing your design for full manufacturing. There are other options, in part called Tiny Tapeout, offer the part frame called Caravelle, where you can put different designs and submit for manufacturing. I will come again to Tiny Tapeout in a few slides. There are a lot of online resources introducing OpenPDKs, not only IHP, but Skywater Global Foundries. Here there is example developed by Professor Boris Murman, who is now with University of Hawaii. Just follow the link to get all the online resources. Digital design, it's simple. Okay, it's not the right expression, but has complete digital design flow, starting from Verilog high-level description and appropriate libraries. You go through this complete synthesis, full plan, flow planning, placement, clock optimization, up to down to final layout. This flow, it's fully automatized with different tools and basically does not need human interaction at each step. There are plenty tools like Kiosis, ABC, OpenRoad. For digital synthesis, we recommend K-Layout for layout verification. Just follow the link below. In Europe, we have a couple of tools developed by Leipzig's laboratory in France. They provide alternative to Yosys and OpenFlow. Professor Prettel and his team at University Linz in Austria they provide a lot of information guiding you through digital design flow, starting with schematic entry, looking at the layout, following all the verification validation task, using a Verilog, going down to OpenLine or OpenRoad, preparing your design for submission. Analog RF design flow, it's not fully automatized. We have set of or subset of open source design tools. For IHP OpenPDK, we are recommending QuaxS as alternative to eSimM for schematic entry. In both cases, QuaxS or eSimM, we are using ngSpice or Zeiss for transistor level, spice level simulation. Entering your schematic, running simulation, we are coming to the circuit layout drawing, K layout, and Magic as alternative are offering all the tools for device design rule checking, LDS, completing this loop. You are coming to the point of parasitic extraction to validate your circuit. If you need something more specific about your RF passive components, you can access OpenEMS. It's open source electromagnetic simulator, fully integrated with the flow for passive component verification, like transmission line, interconnect, spiral inductors, or integrated antennas. QuaxS, it's our central schematic entry editor with ngSpice or Zeiss running in background for transistor level simulation. Here there is a very simple single transistor layout with all data visualization you can access following the transistor level simulation. The tool was introduced at a couple of workshops, including presentation recently at SDEC conference. Here there is yet another snapshot of quark simulation. Again, simple MOSFET transistor or basic inverter block simulated transistor level. We are recommending K layout, but and Quarks for schematic entry. But of course, there are other alternatives in free open source software domain. eSimM, it's for schematic. Just follow a link to download the tool. Or Magic, it's quite advanced GDS layout editor. You can access following this link below. There are a couple of other tools, alternatives to Magic or Kout. The Revolution EDA, they are developing fully integrated design flow, including not only schematic editor, but also layout editor in one package. At the moment, it's on qualification. We do not have full benchmark for RF EDA tool. There are plenty of tools available online. You do not need local installation. You just follow links. Here we have a really nice teaching education tool called Sylvis, which allows you to start with device or cell layout. Here, I'm sure you are recognizing basic inverter block and its layout. You can move here this hair cross line to see cross section, and I'm sure you are recognizing metallization input line with contacts touching poly in red, and then the output metallization here in this cross section on the inverter output. Creating layout, you can generate SPICE input deck. Here we have an example of uh, it's inverter SPICE simulation input deck. You can rerun and compare this. Again, all this is available online without a need to install any tools locally. KiCad, it's a great tool for PCB design. It's not really part of OpenPDK design flow, but after completing IC design, manufacturing your chip, you would need to design PCB test board. And KiCad with ngSpice running in the background is one of the best choices. So again, follow link below to learn more about KiCad and ngSpice simulations for the fully integrated with KiCad. There are more and more tools available online. This is a IT CAD, which include schematic capture and also PCB layout editor. I mentioned about EMS. If you are RF designer, you can benefit validating your RF components using 3D electromagnetic simulations. Initially, OpenEMS was designed to analyze external antenna running complete 3D electromagnetic simulation. We adapted EMS as a part of our PDK, and we have full integration here in this flow. After entering your schematic, identifying RF components, you can move to OpenEMS, going from layout to 3D representation of your passive components. Here we have a simple example of spiral inductor. You complete 3D electromagnetic simulations. As a result, you're entering your data to schematic and completing this flow for your full analog RF simulation. Here there is just an example of simulation of spiral inductor for given GDS2 layout. Again, each slide has links and pointers to further documentation. So in particular, recent developments where we have optimized and improved Python interface for OpenEMS in our IHP OpenPDK flow. Okay, this is something else. We do not support sensors or MEMS developments, but if you are in this domain, you can find also open source tools to run complete 3D sensor or MEMS simulation. This is just one of the example I found online where you can use open source tools to run numerical simulation of simple optical scanner, kind of floating mobile mirrors. Now we are coming to quite important part of OpenPDK, compact SPICE models, they are critical for to maintain the high quality of OpenPDK, transistor level SPICE libraries, and all digital reference libraries. To introduce new SPICE compact model, we are recommending Verilog as a modeling language. This is just one slide where I'm introducing AKV long channel Verilog model code. And if you are familiar with other programming languages, switching to Verilog is a simple task. You see all basic variable definition, main blocks where you're entering analytical expression to model your devices. Here we are modeling a very simple long channel MOSFET model, defining its current in Verilog. Having a model on, okay, this, maybe I will skip this. It's about AKV model application for cryogenic temperature level simulations. You can review all references afterwards. Having defined your model, I was showing a MOSFET example, but using Verilog A, you can define any device, semiconductor device, active components or passive components, including resistor, capacitor, spiral inductors. Starting with Verilog model code, we are using open source Verilog A compiler, which generates the dynamic library for ngSpice or Zeiss. This process is virtually transparent to user and gives a high quality, very fast dynamic library for new device, ngSpice or Zeiss simulation. Just follow all the links to learn about ngSpice. Of course, there is always an alternative. GNU-CAP is developing their own Verilog AMS simulation tools, and it's now benchmarked for IHP OpenPDK. Defining model in Verilog A, compiling for transistor level simulation, ngSpice or Zeiss. This is transparent to user. On the left, you have a very simple input deck to simulate transfer characteristics. All what you need to do to call a Verilog model just to have one extra statement. So this task is fully transparent to a designer or ngSpice user. As I mentioned, SPICE compact models are critical. So we are also supporting dedicated test chip to analyze device performance, look at the device statistics, in particular in the device matching, which is critical for analog transistor level design. We are about to implement new test chip for, in this case, matching evaluation. Measurements, it's quite critical. Advanced test equipment is quite expensive, but you can start with open hardware test equipment for basic lab measurements. Here you can see very like post-stamp size PCB with complete measurements equipment. This includes the function generator, two-channel function generator, two-channel scope digital analyzer. Just for a couple of US dollars or Swiss francs, you can buy this tiny board. I connected a very simple CMOS inverter, apply the signals, and could visualize inverter output. There are more advanced chips for transistor measurements and characterization. Mobius project offer a huge matrix of 65 by 10 transistors, which you can use to configure it not only single transistor, but basic analog blocks for measurements and characterization. This project is coordinated by Professor Kidnet, and we are about to also implement this using open PDK at IHP. The further details just follow. It's a great teaching education tool. All what I was presenting, IHP technology, OpenPDK, complete digital and analog RF design flow. It's not virtual. At the very end, we are ending with chip design, which is submitted to IHP for manufacturing. And here, there are a couple of recent projects with working silicon chip. Of course, IHP was one of the very first to put open source, open PDK design. Here we have open security hardware module design with open EDA tools using open PDK and implemented and manufactured using IHP facility. Top left, it's snapshot of circuit design, and just below you can see IC put on the test board and successfully measured and characterized. We have partners at ETH in Zurich. They are expert in digital design and submitted a couple of quite advanced implementation of 65 RISC processors, fully designed with open source tools implemented using IHP, OpenPDK, manufactured and successfully tested. This is yet another. It's more complex with 2 million gates. It's full Linux bootable RISC-V SoC implementation using IHP process. Just follow links below to learn more about this particle design. I was already referring to our partners at Technical University in Linz. They start using Skywater, but now they are porting all this they design into IHP 130 nanometer by CMOS process. They also are expert in analog RF design, recently submitted full analog RF test chip for RF microwave applications. To design the chip, they were using a very advanced open source tool called GDS Factory, which is a huge set of Python libraries allowing complete design automatization. As you see, all what you have on the left-hand side was generate just purely coding layout without any human interaction. I was referring to Tiny Taper. This is an alternative mainly for digital design. This year, we were running 2 tiny tapeouts at IHP. The next one for 2026 will be available in March, and still the dates to be defined. Here, very simple example, one of I think 500 examples submitted to each tiny tapeout. It's kind of mini RISC-V implementation done by just one designer from A to Z submitting to IHP. Just follow the links to learn more about tiny tapeout and this particle design. Again, digital design has a complete automated design flow. We do not have such solution for for analog RF design, and currently working with our partners at Infineon in Austria, who already established a modular analog RF design flow. At the moment, they are focusing on proprietary PDKs and commercial tools, but adding slowly open source, free open source software flow for all the tasks. It's work in progress. It's still maintained despite of being open source internally at Infineon, but we are expecting complete open source release very soon. In Europe, we have other alternative for analog design automatization. This is developed by LEAP6 laboratory at Sorbonne University, coordinated by Jean-Paul Chaput. If you would like to join this initiative, just contact Jean-Paul. This is yet another attempt to automatize analog design flow. Ligent, it's a tool developed at Minnesota University. They were working with Intel to make a very first implementation, and as you see, they start using proprietary PDK as well, huge set of database for machine learning, which belongs to Intel. I hope very soon this can be extended and all elements should be available in open source tool. Couple of book recommendation. This is a great book by Professor Pretel, introducing you to all design tasks, basically starting from Python coding of basic IC blocks through accessing PDK, placement, routing, reviewing simulation and experimental data. I'm strongly recommending this book for all hackathon participants. What next? We have already IHP with OpenPDK. There is a great initiative project, one student, one chip in China. Japan is joining with very first kind of laboratory PDK called Minimal Fab. OpenSUSHI is discussing OpenPDK project with their partners across Japan. There are other groups like IEEE Solid State, CAS, they are very active. I'm sure you're familiar with this IEEE initiative. Digital design is dominated by a variety of RISC-V implementation. So if you're digital designer, you should have a closer look at this CPU implementation. In Europe, we were trying to coordinating open source EDA development, and a huge group of experts defined the open source EDA roadmap for Europe. This was mainly coordinated by FOSSI Foundation. And as a result, we defined three main actions in this roadmap to support analog and mixed signal design, uh, help in productivity, interoperability, and verification across the Europe. And we are even looking beyond basic IC design, uh, trying to support system-on-chip innovation. This task or actions has been recognized by European Commission, which leads to new EU-level R&D project, and we hope we will join one of the very soon. Okay, unfortunately, this OpenPDK, free OpenPDK multi-project wafer run has been closed, but we are opening new early next year. As an alternative, we still have optional run in November, which can significantly reduce the cost depending on number of submissions. All what I was presenting, it's a huge team effort. This list, I'm sure, does not include all contributors. At IHP, I would like to acknowledge René Scholz, who is leading OpenPDK initiative. We have already interacted with ETH in Zurich, University in Linz, and I'm really happy having a lot of discussion and interaction with all your team at IIT Mumbai. All has been generously financially supported by variety of German funding organization, including Federal Ministry of Education and Research. Open source EDA roadmap, it was also huge team effort led by top-level internationally recognized professors across the Europe and quite experienced designers. I was promoting OpenPDK across the different event, not only in Europe, but internationally. Again, I'm really happy to join your eSIM marathon, and I hope there will be some further interaction quite soon. Yes, by this, let me close my presentation and eventually discuss or answer any of your questions you can have now.
Yeah, thank you, Vladek, for your wonderful presentation. So I would like to add, like, Vladek has been associated with us for last few many years, and yeah, he visits India quite often, and he also invited me and Professor Kanan for the Free Silicon Conference and the Mixed Desk Conference at Germany and Poland, respectively. But we couldn't go due to some visa restrictions. Yeah, but he
Yeah.
has been a good friend of us since long, and yeah, I would ask you all to ask questions related to OpenPDK, ISP, and different other things over this chat box. So one interesting question they were asking, like, which schematic editor spice combination is recommended for front end analog RF design? XM, ngSpice or Cox?
Uh, in particular for IHP OpenPDK, if you are analog RF designer, we are recommending Quarks. Quarks is kind of integrated environment where you have full schematic editor accessing all open IHP OpenPDK libraries. We provide all symbols for active and passive components and completing circuit schematic editing. You can run ngSpice transistor level simulation. ngSpice access to qualify uh, Spice libraries for IHP 130 nano by CMOS process. So all has been silicon verified. Complete schematic entry and transistor simulation. You are moving to K layout. We recommend this tool for IHP OpenPDK. It has complete set of verification validation scripts, including design rule checker, layout versus schematic, and parasitic extraction. Moreover, for specific RF application, we have a link between the K layout cell representing, for example, passive components to access and run numerical simulation with OpenEMS. Uh, so all these basic tools has been verified, validated for IHP OpenPDK. Of course, if you are familiar with other tools like eSimM for schematic entry, Magic for layout editing, yes, you can also use this, but this is like second level or second recommendation from our side.
Yeah, so again, he's asking Vipul, his name is. So, does XM and Spice support all RF analysis like SP, HB, PSS, etc. for IHP PDK?
Uh,
Or are these?
we support basic DC, AC, and transient. There is additional project to include uh, harmonic balance, uh, which is not fully, or it's not supported by ngSpice. ngSpice or IHP OpenPDK has been verified for ngSpice and Zeiss. So if some simulation options are not available in ngSpice, you can easily switch to Zeiss and access other simulation options.
Okay, and someone is asking about simulation for Verilog A.
So at transistor level, we have Verilog A simulator. If you have a new transistor model or other active or passive Verilog code for your model, you can compile and access through ngSpice. We do not have full Verilog circuit or sub-circuit simulator. Maybe if you want to have a more technical discussion, just use my email and submit your questions. So Verilog A or Verilog AMS, it's not fully supported. For digital simulation, we have a full sub-circuit Verilog simulators, but not with A or AMS option.
Yeah, I hope all the questions are answered. Anything else, participants? Yeah, how to perform mixed level signal simulation for digital analog RF blocks and designs. So I would like to answer for digital plus analog. We already have the feature available in eSIM by combining ngSpice and Verilator, but plus RF blocks, I would want Vladek to answer.
It's always question what you mean by RF blocks. If this is, let's say, LNA input amplifier or PA, these are usually just a few transistors at RF, and this can be easily simulated as individual RF blocks. Question how to okay, LNA, RF mixer, PA. This part does not include digital simulation. But as you mentioned, you have eSIM or validator integration. So I guess this could be combined. My email is in the slides, which will be distributed, but just for your reference, I put my email to the chat window. I guess in the hackathon program, you will have also other presentation of ngSpice simulator by Professor Vogt. He at also X-Spice option to ngSpice, which would allow transistor level and digital block co-simulation. So it's kind of mixed mode simulation. So you can continue this discussion or ask further questions to Professor Vogt or drop me email with everything else.
Okay, any other questions related to OpenPDK and IHP fabrication? So I hope to see lot many submissions coming out fabricated from ISP over the time. Yeah.
Yes, this would be great to have a couple of design coming as a result of your hackathon or
Mm.
eSIM marathon, and surely we will try to find the best, most economic option to manufacture your chip. So
Yeah. Okay. So thank you. Thanks a lot, Vladek.
you are welcome.
Yeah. So
Again, you have my contacts, and I'm looking further to further interaction with you, all the hackathon participants, and crossing fingers for first first integrated circuit manufacture.
yeah. So in fact, I also found lot came to know about lot many things from your slides. So thank you. So I will be presenting now. So also you are there on the Slack channel. If someone questions you, please feel free to answer or something.
If you don't mind putting your the link to your or pointer to your Slack channel, so I can join and eventually answer the
Sure.
basic question about IHP OpenPDK or tools which we are recommending.
I have pasted the link over the chat box. I will also.
Okay, yeah, I will try to join just afterwards. So.
Uh-huh. Yeah, okay. So in next couple of minutes, I will be demonstrating like how to access the videos and how to see the lectures available. So yeah, so we would be following a platform called as Bodhi 3, which is developed at IIT Bombay, and so you will get a similar kind of mail like so how to get started, pointed to the dashboard of a course, and this is the course name. And yeah, so once you get these links, let me show you. So you can copy this or click this, and let me try it out on the private windows. So once you open it up, it will redirect you to the Bodhi 3 page, and you can log in here by giving your email ID, but you will not have your password at the start, so you can change it and by giving your giving in your email ID, and a reset link will be set to your email. A recent reset password email will be sent to you, and you can reset your password this way. So after you have your password resetted, then you can use your email and password and sign in. And after you sign in, you will get a page something like this, and this is the interface. And yeah, here, so we are still uploading some of the things. So here are the videos available. So the IHP PDK installation. So click on it, and you will be able to access the video and some other files. So some example netlist files, then installations, shell script, and so on will be available over here. And there is another thing. So running a simple CMOS example circuit with eSIM and IHP PDK. This is also video. So yeah, so check these things out, whatever is shared over this. And later on, we will show you how to submit the final stage files. It will be through labs or quizzes. So we will share all the details to you. So we by tonight we will be sharing the link, this mail tonight or tomorrow. We will be sending the link to join this Bodhi platform. Okay. So I hope I am clear with all these things. And if you have any doubts, you want any resources, please feel free to contact us. And definitely all the resources for IHP and eSIM are available over the internet. You can check out the documentation and different other things. Ladakh has shared an excellent presentation, which I will be sharing to you, and it contains most of the links. So yeah. So anything else you want to mention? Any queries? Anything related to the submissions and things like that? We'll be sharing the mails. So once you get the mail, receive the mail, you can explore the platform of both the three. Okay. And we have some two TAs, Chandru and Ashwarya Sinha. So they may be helping you, who helped us to create these videos. So they may also help you to share your to solve your doubts and queries related to HP installation and eSIM. So for now, you can begin with the eSIM installation. It's straightforward, and ISP also you can start off by referring to some documentation. We will share the videos. Anything else? Any queries? So yeah, so this Bodhiti platform will be available to only those who have submitted the literature survey forms, literature survey reports, not others. So that is the first qualifier stage that you need to clear. Yeah, so hope I am clear with all the things.
Okay, great. Again, thank you very much for organizing, sharing recent updates, and I guess we'll be soon joining uh, other NGSpice presentation by Professor Vogt. So keep me in the communication loop.
Yeah, yeah, sure, sure. We will keep you in the loop, and yeah, so we will keep everyone updated regarding what's happening later. So next webinar meeting will be hopefully with Professor Holger, and in between we can have a webinar for exploring the videos. We'll let you know. Okay.
Okay, perfect.
Yeah.
Again, thank you very much. Have a great evening. Bye for now.
Yeah. Thank you. Thank you all. Bye.